Hello, and welcome back to RRS Live. My name is Sawaya. I'm a junior majoring in mechanical engineering, and for the last semester, I've been working with Dr. Agrawal in the Engines and Combustions Lab in the Department of Mechanical Engineering on the effects of variable radii on detonation wave propagation through curved regimes. So, to begin, let's talk about the importance of clean combustion in the modern day. So, everything we use on the day-to-day, from our phones to our computers, our homes, and soon to be even our cars, require electricity. And in 2017 alone, we produced 4.01 trillion kilowatt hours of electricity, and 63% of which was produced by some form of combustion-based energy production. And with all this in mind, combustion will continue to be such a major source of energy for us, and we need to continually be trying to find more efficient methods of combustion to use for energy production. And one way we can do that is by taking a closer look at combustion itself. So there's two main forms of combustion. The first is deflagration, and the second is detonation. So for deflagration, we have three main parts. We have the reactant mixture, which consists of our fuel and our oxidizer. We have a flame front, and then we have our burnt and gaseous products. And this flame front goes and propagates through the reactant mixture at a little bit less than 100 meters per second. And it converts this reactant mixture into the gaseous products and some heat that we can go and convert into usable energy like electricity. On the other hand, we have detonation. So this looks very similar. We have a reactant mixture again. We have some burnt gaseous products. But instead of a flame front, we have a shock wave and a reaction zone. And this shock wave and reaction zone travel much faster than the flame front, about 2,000 meters per second, multiple times the speed of sound. And the main difference that we have is that there's actually a pressure increase over this reaction. So the burnt gaseous products are at a higher pressure than the reactants were. And this higher pressure can be converted more easily into usable work. So this allows us to have a higher efficiency for systems that utilize detonation over deflagration, roughly a 6 to 7% efficiency increase for a combined cycle system. However, the big difficulty with this is finding ways to implement detonation into these energy-based production systems. One way that we can actually do that is by utilizing a rotating detonation combustor. This would take the place of current combustors used in natural gas turbine power plants. These combustors consist of three main parts. There is the center body, the outer body, and then the annulus. The annulus is the channel between the center body and the outer body, and it's actually where the reaction takes place and we actually burn our reactants. So let's take a closer look at that annular region. So in the blue, we have our fresh reactants that are constantly being pumped into the combustor from the bottom. Then we have our red line, which is our detonation wave, which travels around the center body multiple times per second, about 6,700 times per second, about 2,000 meters per second. And then we have our yellow expansion zone behind that, and that's our burnt products. And those will be pushed out of the combustor by the reactants that we're continuously pumping in, and then the detonation wave will continue to propagate around. And one of the main benefits of rotating detonation combustors over other detonation-based combustors is that they're actually very simple. So they do not require a very large amount of complex valve timing or valves in general. But there's a very large area of research that is lacking on these combustors. And that main area is the effects of different geometries of these combustors on the detonation wave propagating through them. So the three geometries we are concerned with is radii, channel width, and channel height. And then we want to also see the effects of various fuel conditions on the detonation wave in these different geometries, mainly the pressure that the fuel is being introduced at and the mixture of fuel and oxidizer. So we could go through and make multiple different detonation combustors, but that would not be very cost effective. It would also take a very large amount of time. So instead, what we have designed is a spiral system. So this allows us to test multiple different radii at the same time, and it being a modular system as well, we could actually have multiple different spirals, which will allow for us to have different channel widths and channel heights as well. And then we're going to have a full valve system leading into the spiral that allows us to control the fuel pressure and then the mixture that is going into the spiral. And then the final thing is that this spiral will actually be optically accessible. So we could use different optical analysis techniques to study the detonation wave, how it's propagating through the spiral, ways that the geometry is affected, the pressure and mixture affected, and gain a lot more data than we are able to currently with regular detonation combustors, rotating detonation combustors, since the annular region for those is not easily optically accessible. So for the system, there's two main parts. There is the mechanical system, which consists of our supply cylinders. That has all of our reactant gases in them. So there's three different supply cylinders, and all three of those feed into our storage tank, which we use to mix our three gases before we go and introduce them into the spiral system, into the spiral itself. We have a vacuum pump. This removes all the air from the system, so we have a constant baseline that we can start from for each test. So we know exactly what's in the system before we start introducing fuel and reactants and things like that. And then we have our deflagration and detonation transition tube. All the way on the left end of this, we have an automotive spark plug that introduces a deflagration event, so just a small burning event. And as it travels down this very long tube, it actually transforms into a detonation wave before it enters the spiral. And then, of course, we have our spiral. This is where we will be doing the majority of our data collection. And it's mounted on an optical breadboard table, so we can actually mount our optical equipment on that as well. But between all of these components, we have multiple valves. So we need a way to control those valves, and that's where my role for the project comes in. So I am making the control system in LabVIEW for this mechanical system. So there's two main parts to this. There's the valve control side, and then there's the data acquisition side. So for the valve control, we have our two priorities are remote operation and precise operation. We want remote operation because we are dealing with a combustible mixture in a confined space. So if something did happen where we had a spark within the system where we didn't want it to, we don't want to have a dangerous event on our hands. So we want to make sure that we are outside of the test cell and not near the system whenever we are running tests or when it is pressurized. So by having this automated control system, it allows to be outside the test cell and operate all the valves from there. And it'll also allow for precise operation of these valves. Some of our operations that we use while running the system require very specific timings for valves, and that'd be very difficult for one person to do with multiple different valves in different locations. So this allows us to actuate multiple valves at a single moment by a single press of a button instead of going through and doing all of them by hand. And then there's also the data acquisition side. Currently, we only have pressure sensors within our system, but eventually we are hoping to put in thermocouples, which will give us temperature readings as well. And then further down the road, we will implement our optical analysis techniques, which is where we will be getting the majority of our data from. So our goals and future steps, we need to install a mechanical system within the test cell, and then we need to go and verify the system with inert gas. And that will allow us to see if there's any leaks within the system, if we're losing pressure, and to make sure that all of our valve operations work as expected. And then once we have done all that, and we know that the system will work, we can begin performing our parametric study on detonation wave behavior through these multiple different geometries. And with that, I'd like to take any questions.
Could you speak more to some of the optical analysis techniques that you'll be using?
So we will be using two main different optical analysis techniques. The first will simply be high-speed videography. That will just give us general information like the speed of the wave, the cell structure within the wave, how long the wave lasts within the spiral, and other kinds of information. And we also be implementing higher-level optical analysis techniques like rainbow Schlieren deflectometry, which will provide us with density gradient information about the wave as well.
John, you mentioned on slide 6 that varying the radius is an important characteristic. Why is radius such an important characteristic?
Okay, so the radius is a very important characteristic to us because it will determine how the different sizes that we can make these combustors. So we currently know that there is a critical radius at which detonation cannot be sustained. However, we do not know what that critical radius is and how different channel geometries, pressures, and fuel ratios will affect that. And knowing that critical radius will tell us the smallest combustors we can make, which could open up other applications for these kind of combustors.
What type of reactant gases are going to be using?
So we are using three main gases within our system. We are using methane, which is our fuel, pure oxygen, which is our oxidizer for the fuel, and then nitrogen, which is our inert gas, which will be simulating regular atmospheric air.